Hey guys, welcome back. Alright, at this point we know that a limit is a y-value approach, the limit of a constant is the constant, and the limit of x as x approaches any number is the number. Now hopefully you're taking notes, and I want you to start a brand new fresh sheet of notepaper, and we're going to make what I call the limit chart. Turn your notepaper landscape style so that it's nice and wide. And at the top, if you want to write limit chart, you can. But then underneath that, we're going to write to evaluate a limit. To evaluate a limit, the first thing you do is substitute. And if substitution works, then cool, you're set. And we also know that if we wanted to, we could quick sketch the function. If we have a good quick sketch to look at, then we can just look at the quick sketch and figure out the limit graphically. But like we talked about last time, substitution doesn't always work. And if it doesn't work, you might get something like 0 over 0. So on the left side of your limit chart, bring a branch all the way across, and then cut back about halfway. We're going to come back to that in just a bit. Now keep this limit chart separate and go back to your regular notes. And let's look at a problem like this. Alright, to evaluate this limit, the first thing I'm going to do is substitute. And if substitution works, then cool, I'm done. So I plug in 2 squared minus 4 over 2 minus 2. I get 0 over 0. Substitution did not work, not cool. But we can deal with this. 0 over 0 is what we call indeterminate. Indeterminate basically means that we can't determine a limit that makes sense yet. So switch back to your limit chart. At this halfway point, we're going to write 0 over 0. It's called an indeterminate limit. And an indeterminate limit means 3 things. Number 1, it means there is a limit. But I must manipulate the function to find it. Manipulate meaning change it around, fix it up. And third, it means there is a removable discontinuity on the function. Again, an indeterminate limit means 3 things. There is a limit, I must manipulate the function to find it, and there's a removable discontinuity. To deal with this, we have a few different options. The first idea is to factor. Once we factor, we're going to cancel out a term and then resubstitute. This process is essentially the same as the work that we did when we were graphing rational functions. Remember problems like this? The idea was to sketch them. Step 1 was always to find the domain. So we say the bottom can't be 0, and we get x can't be negative 3. Step 2 was to find the type of discontinuity and where it occurred. To do that, we would plug in the value for the discontinuity. And for this problem, we get 0 over 0. That meant there was a removable discontinuity at the x value, and we needed to find the y value of the removable discontinuity. To find the y value of the removable discontinuity, we came back to the original function, and we would factor, then cancel, and then substitute our x value into that new factored canceled version. When you factored, you always found this matching top and bottom term where the x value would have created a 0 over 0. We were basically canceling away the problem terms. Once you had the factored canceled version, you'd plug in the x value, and you would find the y value for the removable discontinuity. Again, that's basically what we're going to do now. Going back to the problem that we had right here. We substituted, we got 0 over 0, and we know that's an indeterminate limit. That means there is a limit. I must manipulate the function to find it, and there's going to be a removable discontinuity. And to deal with this situation, the first thing we're going to do is factor. And just like with the rational functions, you will always find matching top and bottom terms. That's what made this problem indeterminate in the first place. So you cancel out the problem terms, you cancel out the terms that create that 0 over 0 problem that we have, and now we have a new look to our limit. At this point, we simply resubstitute, we plug in the value that we're approaching. We get 2 plus 2. That equals 4. 4 is our limit. We know that approaching 2 in the actual function causes a problem. So that's called a restriction. Our x value cannot be 2 because there's a hole in the function at 2. And that hole specifically occurs at 2, 4. It's the restriction and the limit. Indeterminate limits will always include these three parts. There's the limit itself, then the restriction, and then the removable discontinuity. Oftentimes, they only want to know what the limit is, but the restriction and the removable discontinuity still exist. You just might not have to state it in your answer. Try this problem. Always substitute first just to verify the type of problem we're dealing with. And we do, in fact, get 0 over 0. Let me ask you this. What is 0 over 0 called? It's called indeterminate. And what are the three things an indeterminate limit means? It means there is a limit, I must manipulate the function to find it, and there's a removable discontinuity. And to deal with that, what's the first thing we can do? We factor. Then we'll cancel and resubstitute, but factor is the word that you really need to remember. So we're going to factor, then cancel and resubstitute. So you try this and come back when you're ready. All right, here we go. You will always have the matching terms top and bottom. So if you're having trouble factoring, keep in mind that one of the factors is going to need to be the bottom term. That kind of gives you a little hint when you're factoring. The matchy-matchy 0 over 0 terms will cancel always. And now my limit has a new look. You do have to drag this limit as x goes to -3 part with you throughout the entire problem until you finally substitute and get rid of the x. So right here, I'm going to substitute the -3. I no longer have to write the limit as x approaches -3, and I get -5. That's the limit, and we automatically state that there's a restriction of x can't be -3. And there's a removable discontinuity at the restriction comes first, then the limit. And like I said a moment ago, you won't always be asked for all three parts. If you just were asked to state the limit itself is -5. But these other two elements also exist, so it's good practice to think about them too. Try this one. Try it on your own, come back when you're ready. To evaluate a limit, the first thing I do is substitute. And when I substitute, I get 9 minus 9 over 3 plus 3. That's 0 over, 6. That's just 0. 0 divided by 6 is 0. And 0 is a number. Substitution worked. It's cool. There's no need to do the factor, cancel, resubstitution process. That's why it's always important to substitute first. Sometimes it doesn't look like it's going to work out, but it works out just fine. Now let me change it slightly and you can try again. Give it a try, come back when you're ready. Okay, we've got -3 squared minus 9 over -3 plus 3. This one is 0 over 0. This is an indeterminate limit, and I know that means three things. What are the three things an indeterminate limit means? There is a limit. I must manipulate the function to find it. There's a removable discontinuity, and to deal with that, I'm going to factor. That's right. Okay, so from here, I'm going to factor this term on top. I see the matching top and bottom terms where if I were to plug in the x, I would have 0 over 0. Those are my problem terms, so I cancel those away. Now I have a new look to the limit. I can substitute, and I get -6. That's my limit. My restriction is that x can't be whatever I'm approaching. Whatever I'm approaching, that's my restriction. And then the removable discontinuity, the hole in the graph, will always be the restriction, and then the limit. Now sometimes the problems get a little more involved, where straight factoring won't do the trick. Something like that. Now if you're good at cubic factoring, this very well could be a factoring problem, but not everyone remembers their cubic factoring. And what if it wasn't a cubic? What if it was a quartic or something higher? How would we deal with it then? Well, let's start at the beginning. Let's not get ahead of ourselves. To evaluate a limit, the first thing we do is substitute. It equals 0 over 0. That's an indeterminate limit. I know it means three things, and I know to deal with that, I'm going to try to factor. But again, if you're not great at factoring cubics, or if it was a higher power than a cubic, what would we do? Well, let's come back to our limit chart. All right, I've made a standalone limit chart. It's its own page in my notebook, and I'm going to keep it separate from the rest of my notes. Maybe it's a problem that won't factor, so we're going on to option number 2. Option number 2 is polynomial division, and then we'll cancel and resubstitute. Coming back to the problem, the first question might be, well, what term will I divide out of the polynomial? Keep in mind, we have problems with the 0 over 0 term. X plus 2 will create that 0 on the bottom for us once we've plugged in an x value of -2. So x plus 2 is the term that we want to divide out of the polynomial. If it's the type of problem that synthetic division will work on, then go ahead and use synthetic division. Synthetic division would work just fine on this problem, but I'm going to go with the longer version of polynomial division. I should get a remainder of 0. I should always get a remainder of 0 for these problems. And what this polynomial division means is that x plus 2 times x squared minus 2x plus 4 will equal x cubed plus 8. So I'm going to rewrite my limit. And you'll see that once again we have the matching terms, top and bottom, that would create the 0 over 0 that is a problem for us. We're going to cancel those terms away. We're going to rewrite the limit. Again, dragging this limit as x approaches term with us all the way until the point that we substitute and have no more x's. So I'm going to go ahead and substitute here. I get 12. I know there's a restriction that x can't equal the value that we're approaching, and then there's a removable discontinuity at the restriction and the limit. Polynomial division is just fancy factoring, so it's basically just another version of our first idea. But look at a slightly different version of this same problem. Everything's the same except for the denominator of the function. Let's go ahead and substitute. We get 0 over 0. Then if we dive straight into polynomial division using these exact terms, we run into a pretty hefty remainder in this problem, which means that we didn't divide away the right term. But looking at the problem, those are the terms that we had. Well, this problem is fixable when we realize that we just need to break the denominator down. See, x squared minus 4 is factorable, and only one of the terms causes a 0 on the bottom. If we were to factor x squared minus 4, we see that we get x plus 2 times x minus 2. And if we plug a negative 2 into x minus 2, that's negative 4. That's not 0. That's not a problem for us. So the only problem term that we have is x plus 2. So we would only divide out the x plus 2. It would look like this. So now we see the matching terms on the top and bottom that give us 0 that cause us a problem. So we cancel those out, we rewrite the limit, and then we substitute. We get a limit of negative 3 with a restriction that x can't be negative 2, and that means there's a removable discontinuity at negative 2, negative 3. Let's look at our next problem. All right, to evaluate a limit, the first thing we do is substitute, and if substitution works, then cool. So let's go ahead and plug in 3. We get rad 4 minus 2 over 0. That's 0 over 0. 0 over 0 is called what? It's called indeterminate, and it means 3 things. It means there is a limit, I must manipulate the function to find it, and there's a removable discontinuity. And to deal with that, I'm going to try to factor. But no, not with this problem. And if factoring doesn't work, then I might try polynomial division. But again, no, not with this problem. That leads us to option number 3. Option number 3 on our limit chart is rationalize by the conjugate. And then cancel and resubstitute. This is the option used most often when you have a radical in the problem, assuming, of course, that straight substitution doesn't work. So coming back here, let's take a look. Let's start fresh. The conjugate of rad x plus 1 minus 2 is rad x plus 1 plus 2. We just changed that middle sign. I'm going to multiply top and bottom by the conjugate. It's just a fancy version of 1. Dragging the limit with us. On the bottom, I have x minus 3 times rad x plus 1 plus 2. Just keep those separate. Don't FOIL them together. Don't multiply them together. Just keep those terms separate. On the top, I am going to FOIL these terms together and see what we get. My first terms give me x plus 1. My outer terms give me a positive 2 rad x plus 1. My inner terms give me a negative 2 rad x plus 1. My outer inner terms cancel away, as they always should with a conjugate. And then my last terms give me a minus 4. Simplifying the top, I have the limit as x approaches 3 of x minus 3 over x minus 3 times rad x plus 1 plus 2. Now again, you see the matching terms top and bottom, where if I plugged in the value that we were approaching, we would get 0 over 0. I'm going to cancel those problem terms, and that leaves me with the limit as x approaches 3 of 1 over rad x plus 1 plus 2. The problem terms have been canceled away, so I'm going to go ahead and resubstitute. At this point, I can finally stop writing the limit. Once you substitute the x away, you don't have to write the limit part anymore. So I have 1 over rad 3 plus 1 plus 2. That's 1 over 2 plus 2. My limit is 1/4. My restriction is x can't be 3. There's a removable discontinuity at 3, 1/4. Now you try this one and see what you get. Come back whenever you're ready. All right, to evaluate a limit, I always substitute first. I'm going to get rad 2 minus rad 2 over 0 equals 0 over 0. I know it's indeterminate, I know it means three things, and I know to deal with that I can factor, no. Polynomial division, no. Rationalize by the conjugate, yes. So I'm going to start again, and I'm going to multiply by the conjugate, top and bottom. Drag the limit with us, and just keep the terms separate on the bottom, but FOIL the terms on the top. My outer and inner terms are going to cancel away, as they always should, and then my last terms give me a minus 2. So simplifying the function and rewriting the limit, I get the limit as x goes to 0 of x over x times rad x plus 2 plus rad 2. Now my x's cancel, and now I can resubstitute. I need to rationalize, and I get rad 2 over rad 2 times rad 2 is 2. This 2 was already here, so I get rad 2 over 4. This is the limit. The restriction is that x can't be 0, and there's a removable discontinuity at 0, comma, rad 2 over 4. It's important to realize when looking at the limit chart that these options on the far left are just options. They're not steps. You don't always have to factor first, then do polynomial division, then rationalize by the conjugate. Clearly, not every problem is going to have every one of those steps. They're options, and they can happen in any order in any problem. This is the way I like to think through them, but they won't always be applied in this order. Take a look at this problem. To evaluate a limit, the first thing we do is substitute, and if substitution works, then cool. And I get 0 over 0. So now I think through my options. I could factor, I could use polynomial division, but this problem looks like it's going to be good for rationalizing. So I'm going to multiply by the conjugate on both the top and bottom. And I'm going to keep the top term separate, but the bottom I'm going to multiply through. My first terms give me 5 minus x squared. My outer and inner terms are going to cancel away, and my last terms give me minus 4. So simplifying, I get the limit as x goes to 1 of 1 minus x times rad 5 minus x squared plus 2 over, on the bottom, 5 minus 4 is 1 minus x squared. I've rewritten my limit, and if I go ahead and substitute at this point, you'll quickly see that 1 minus 1 is 0 over 1 minus 1 squared is 0. I still have that 0 over 0 problem term, that term that causes the indeterminate limit. So what can I do? Well, I go right back to my limit chart, and I start again from this point. I could try to factor. And if you see on the bottom, 1 minus x squared, that's a difference of squares. It will factor. So let's go ahead and see what happens. And now I see those matching terms that would cause a problem if we substitute the 1. Those are my 0 over 0 problem terms. I'm going to cancel those away. I'm going to rewrite the limit. And now I'll resubstitute. So I'm going to plug in the 1. I get rad 5 minus 1 squared plus 2 over 1 plus 1. That's going to be rad 4 plus 2 over 2. That's going to give me 4 over 2, which is 2. That's my limit. My restriction is that x can't be 1 because there's a removable discontinuity at 1, 2 on the original function. We're going to look at one more type of problem. We start every problem with a fresh brain with fresh eyes, and we know that to evaluate a limit, the first thing we do is substitute. And if substitution works, then cool. So I substitute 0 in for x. I get 1/2 minus 1/2 over 0. I get 0 over 0. I know that's an indeterminate limit, and to deal with that, I could try to factor, which won't work. Polynomial division doesn't work. Rationalize by the conjugate. Rationalize what? There's nothing there. So what can we do? Sometimes you just need to do it. Sometimes you just need to do what the math is asking you to do. And in fact, that's option number 4 on our limit chart. Option number 4 on our limit chart is to just do it. Attack the problem Nike style. Simply do what the math is asking you to do, and the problem will work itself out. At some point, you'll be able to cancel and resubstitute. Here's what I mean. Looking at this problem, the math is asking us to subtract these fractions. I know that in order to subtract fractions, the bottoms need to be the same. The denominators need to be the same. Let's start again. To make the denominators the same, I need to multiply the first term by 2 over 2, and the second term by 2 plus x over 2 plus x. Now I have common denominators, so when I rewrite this limit, I have the limit as x goes to 0 of 2 over 2 times 2 plus x minus, don't forget your parentheses here, they're super important, 2 plus x over 2 times 2 plus x, all over x. I can rewrite this again. Again, don't forget the parentheses. And I'm just going to keep doing what the math is asking me to do. I'm going to now simplify. And at this point, what I have is a fraction over a fraction. So now the math is asking me to divide these fractions. So I'm going to go ahead and set that up. I'm going to invert and multiply. And now my x's cancel. So rewriting the limit, I get the limit as x goes to 0. Don't lose this little negative here. That's a common problem. And I can go ahead and resubstitute. I get negative 1 over 2 times 2 plus 0. That's negative 1/4, where x can't be 0, and there's a removable discontinuity at 0, negative 1/4. Give this problem a try. Just do the math and see what happens. Come back when you think you have it figured out. And here we go. To evaluate a limit, the first thing I do is substitute, and in this case I get 0 over 0. So starting again, I get the limit as x goes to 0 of 2x over 1 over x plus 4 minus 1/4. And I know my options are to factor, polynomial divide, rationalize by the conjugate, but none of those are going to work. That leads me to my final option of just do it. Just do what the math is asking you to do. The math wants me to subtract these fractions, so I need common denominators. I'm going to multiply the first one by 4 over 4, and the second one by x plus 4 over x plus 4. Don't forget the parentheses. It's a really common mistake, but it'll cause a lot of problems. So now we have the limit as x goes to 0 of 2x over 4 minus, parentheses, x plus 4, all over 4 times x plus 4. Distribute your negative. Simplify one more time. And that leads us to limit as x goes to 0 of 2x over negative x over 4 times x plus 4. Sometimes I like to use a double bar to show the separation of the original fractions, and that might make it easier to see that it's a fraction on top and a fraction on bottom. We have division of fractions here now, so I'm going to keep doing what the math is asking me to do. I'm going to divide 2x over 1 by negative x over 4 times x plus 4. Now I can cancel my x's, simplify the top. Don't lose the negative on the bottom, and in this case we can actually bring that negative up. And now we can resubstitute. Plug in 0 for x. We get negative 8 times 0 plus 4. We end up with negative 32, where x can't be 0, and we have a removable discontinuity at 0, negative 32. Alright guys, I know that was a lot to take in, but as you practice, you'll get really good at figuring out which technique to use for which problem, and the math will become easier and easier. If you have any questions, let me know. Thanks for watching. Have a great day.